Hello and welcome. Today we're going to get right down to the very bottom of it all, the foundation of our entire digital world. We're talking about OSI Layer 1, the physical layer. This is where the magic happens, where the ones and zeros of our data actually meet the real world of cables, light, and radio waves. So here's a question for you. Your computer, your phone, they think in ones and zeros, right? It's all digital, all abstract. But the cables connecting everything, they carry electricity. The fiber optics, they carry light. And Wi-Fi, well, that's just radio waves in the air. So how on earth do those simple ones and zeros make the jump? The answer is the physical layer. It's the ultimate translator between these two worlds. Okay, let's jump right in. To really get a handle on the physical layer, we first have to understand its language. And that language is all about signals. We need to see how it takes that raw data and turns it into something that can actually travel. So officially, the physical layer, or PHY, as you'll often hear it called, is the very first layer of the OSI model. Its job is incredibly important, but also very, very simple. It just takes raw bits, the ones and zeros, and physically sends them. This layer has no idea what the data means, who sent it, or where it's going. It only cares about one thing: moving signals through cables, through fiber, or through the air. The real trick, the secret sauce, is something called signal encoding. This is the process of turning that boring stream of ones and zeros into a physical signal that's strong and stable enough to survive the journey, whether it's across a long cable or through a crowded room full of Wi-Fi signals. Let's look at a classic example, 4B/5B encoding, which you'll find in a lot of Ethernet networks. Now, what's happening here is we're taking a 4-bit chunk of data and we're turning it into a 5-bit code. Now, you might be thinking, wait a minute, why would we add an extra bit? Isn't that less efficient? And that's a great question, because it gets to the heart of why encoding is so clever. And the reason is all about timing, synchronization. See, if you send a really long string of zeros, the electrical signal on the wire might just stay flat. The device on the other end could easily lose track of the rhythm, the clock beat, and misread everything. By using these special 5-bit patterns, we guarantee the signal is constantly changing, which gives the receiver's clock a steady beat to lock onto. It ensures nothing gets lost in translation. And you see this principle in action everywhere. Think about something you probably use every day: Bluetooth. It actually has different physical layer options, different PHYs. You can choose the LE-coded PHY. It's slower, sure, but it can quadruple your range. Or if you need to transfer a big file quickly, you can switch to the LE2M PHY for max speed. It's the same technology, but by changing the physical layer, you're making a fundamental trade-off between speed and range. All right, so we've talked about the how, the language of signals. Now let's look at the what, the actual physical hardware, the toolkit that operates at layer 1. So inside your computer or your phone, you've got a network interface card, or a NIC. Your data's journey starts at the CPU, it passes through another layer, and then it reaches the final boss, the PHY chip. This little chip is the gatekeeper. It's the one that does the encoding we just talked about and turns those digital bits into the actual physical signals that head out the door. And besides the NIC, you have other devices that are pure layer 1. You've got repeaters, which just take a weak signal and give it a boost to help it go farther. And you have hubs, you don't see them much anymore, which are basically just dumb splitters. A signal comes in one port and it gets blasted out of every other port. The thing to remember about all these devices is that they don't think, they don't make decisions, they just move signals. Now, this is where things get really, really interesting. We almost always think of cybersecurity as something that happens at higher layers: firewalls, passwords, encryption. But it turns out the physical layer has its own dark, hidden world of security threats. Here's the thing. Every single piece of electronic equipment you own is basically a tiny unintentional radio station. Your monitor, your keyboard, even the network cable in your wall, they all leak faint electromagnetic signals. And with the right antenna, those signals, those whispers, can be intercepted. And believe me, this is not a new threat. This goes all the way back to World War II, when engineers at Bell Labs realized they could read secret messages from 80 feet away just by listening to the radio waves coming off the encryption machines. Fast forward to 1985, and a researcher named Wim van Eck showed he could see what was on someone's computer screen from hundreds of meters away using just $15 worth of electronics and a TV. This whole field is known as Tempest. And that specific technique he made famous is called Van Eck freaking. It's the art of literally pulling data out of thin air. It's a terrifying reminder that if your hardware is physically broadcasting your secrets, then all the best encryption in the world isn't going to save you. So that begs the question, if our own devices can betray us, how do governments and other high-security organizations protect themselves? Well, they have to build a kind of digital fortress. There are three main strategies. First, shielding. This is pretty straightforward. You literally put the sensitive gear inside a metal box or even build an entire room that blocks radio waves from getting out. Second, you use filtering on all the power and data cables, which stops the secrets from leaking out through the wires. And third is something called the red/black concept. You just have to be extremely careful to keep the red cables carrying sensitive, unencrypted data physically far away from the black cables carrying normal traffic. And just to give you an idea of how seriously this is taken, the highest levels of Tempest security are designed to protect against an attacker who is literally standing 1 meter away, maybe in the office next door. This is security at the most fundamental physical level you can imagine. Okay, let's bring this all home and talk about why understanding this one layer is so incredibly important for everything else. Look, here's the bottom line. The physical layer isn't just another box to check in the OSI model. It is the foundation. Everything, and I mean everything, from your network speed to its reliability to its security, it all rests on layer 1. So why does this matter in the real world? Well, for performance, the next time your internet is slow, the first thing you should check is layer 1. A bad cable, a loose connection, that's usually the problem. For reliability, it's those clever encoding schemes that make sure your data actually gets there in one piece. And for security, well, we've seen it. If an attacker can tap your cable or read signals from the air, your expensive firewall and complex encryption become completely and utterly useless. And that leaves us with one final big question to think about. We're building a world with billions, maybe trillions, of tiny connected devices in our homes, in our factories, everywhere. And they're all broadcasting. The same spooky physics that worried spies in WWI is now happening on a massive scale all around us. So the question for our future is, how do we secure the very air we breathe?
Thanks for watching. Like, share, and subscribe.